Hi class, Mr. Morris. Polarity is actually a really important topic in chemistry, and it goes a lot deeper than what we're going to get into. But we're going to do some notes on polarity. What I want you to know is that it is a significant part of determining what kind of attractive forces there are between molecules. And if you go to study chemistry any deeper in AP chemistry or in college, you're going to find that that's really important in deciding things like how high of a melting point something has, or whether or not it will dissolve in a certain solvent. So there's a lot of really important applications to polarity. What we want to do is define it. Polarity is basically, we're looking at the molecule and we're deciding whether it's got a positive side and a negative side, or whether the electric charge or the electrons are evenly distributed around the atom. In that case, it would be nonpolar. We got to go back to electronegativity to really discuss this. So you remember electronegativity is a snow cone trend. So that means at the top it is the highest and at the bottom it is the lowest. And if we were to tip that snow cone over, then way over here on the right would be the highest electronegativity and the lowest would be on the left. We've omitted the noble gases because they have an electronegativity of 0. Okay, and this is all stuff that we've talked about in the fall semester. But you notice that our highest electronegativity is fluorine, and our lowest electronegativity is over in the bottom left with cesium and francium. You don't need to have these numbers to be able to do most of the problems we're going to give you. But we're going to talk about the numbers just to introduce the topic. So first we want to talk about bond polarity. So that's the polarity of an individual bond. But as you've learned while you're drawing these Lewis structures, most molecules have multiple bonds. They might have 2 bonds or 3 bonds or 4 bonds. They could have up to 6 bonds. So what we want to do is decide the bond polarity, and then we're going to talk about the polarity of a molecule. Let's start with bond polarity. That's a measure of how equally or unequally electrons in a bond are shared. A bond is considered nonpolar when the electrons in the bond are shared equally. It's considered to be polar if they're shared unequally. So we have some examples down here. The way that we decide if they're shared equally or unequally, talking about electronegativity again, remember that's the measure of the tendency of an atom to attract shared electrons towards itself. So if it has a high electronegativity, it's going to attract the electrons to itself more strongly than if it has a low electronegativity. So let's compare a couple atoms, a couple different elements to just kind of get the idea. Fluorine and carbon. So fluorine is definitely more electronegative than carbon is. So if there was a bond between carbon and fluorine, fluorine is kind of going to hog the electrons. It's going to pull them toward itself a little bit more. They'll be still shared in that bond, but more of the time those electrons are going to stay around fluorine than carbon. So you could almost think of it as a tug-of-war match, and fluorine is a little stronger in pulling electrons towards itself. So let's look at these bonds down here and decide if they're polar or nonpolar. Well, I have bromine and bromine. I don't even have to look at the periodic table to know that bromine and bromine are both going to have the exact same electronegativity. So it's going to be a tie. There's not going to be one atom that has more of a pull on the electrons than the other one does. So bromine, a bromine molecule, the bond between bromine and bromine is going to be a nonpolar bond. We usually write NP for nonpolar just to save, to not have to write as much, just to abbreviate it. Okay, let's look at NBr. NBr. So nitrogen is here at 3.0 and Br is 2.8. Well, there's a difference. It's not a big difference, but there's a difference. So we would say this is polar. It's slightly polar. And you could write it out or you could write P. It's fine. Either way. And then H2, hydrogen and hydrogen, again, same element, so that's going to be nonpolar. And then H and S. So H is 2.1, S over here is 2.5. Not extremely polar, but it is still polar. All right, so that's a start. Now we want to use the electronegativity values to explain why the FF bond is nonpolar and the HF bond is polar. Well, the reason is fairly simple. F and F in the FF bond share electrons equally, so the bond is nonpolar. F in HF has a higher electronegativity than H does, so it will attract electrons more strongly. Therefore, HF is a polar bond. It's one way of explaining it. All right, go on to the next part. It says each of the following bonds is polar, so we don't have to figure out if it's polar or not. We want to use the periodic trends in the electronegativity to label each atom in the bond with a positive charge or a negative charge, a partial positive or partial negative charge. So we're going to look at this H and O. We're going to compare hydrogen and oxygen and see which one has a higher electronegativity. That one is going to be more negative because it's attracting the negative electrons to itself. So if we go up to the top, hydrogen is 2.0, oxygen is 3.5. 3.5 is a higher electronegativity, so oxygen will be the partial negative charge and hydrogen will be the partial positive charge. So I'm just going to copy this and paste it right there. Put a couple spaces, and I'm going to copy and paste the negative, partial negative sign right here. All right, and then we get to N and C. Let's look up here. N is 3.0, C is 2.5. So it looks like N is more electronegative. So that's going to be our partial negative charge. And C will be the partial positive charge. All right, now let's look at the IF bond. Iodine is down here at 2.5, F is up here at 4.0. And by the way, what if I didn't have these values? I could still figure it out with a blank periodic table because the electronegativity is the highest at the top of the column and the lowest at the bottom of the column. So I know that fluorine has a higher electronegativity than iodine does, so fluorine is going to be more negative. So fluorine's more negative, iodine's more positive. So iodine's more positive and fluorine is going to be more negative. Silicon and bromine. Silicon is, let's see, right here, and bromine is right there. 1.8, 2.8. Bromine is more electronegative. So silicon is going to be the partial positive, and bromine is going to be the partial negative. I'm just going to copy that because it's exactly the same. And then finally, chlorine and arsenic, Cl and As. Cl is here. As is right here, so Cl and As. We can tell that chlorine's closer to fluorine, so it's going to have a higher electronegativity, and the values say the same thing. So As is the one that's the most or the least electronegative. Chlorine's the most electronegative. So this is negative, this is positive. Let's copy this since it's basically the same pattern. And I'll paste it right there. Okay, the greater the difference in electronegativity between the atoms, the more polar their bond is. That makes sense. We've got a bigger difference between electronegativity, then it's going to be a stronger polar character. So it's going to be more polar. Now what we want to do, we will denote the charge separation. Another way of showing the same thing we did here, positive side, negative side, is using an arrow with a crossed end. The crossed end is the positive side and the arrow end is the negative side. So the arrow always points toward the atom that has a higher electronegativity value. So I think of this as looking kind of like a plus sign. The crossed end looks like a plus sign, it's positive, and the other end points to the most electronegative element. So I've got two of these drawn out here. I'm just going to click it, and I'm going to actually right click and copy the image, and then I can paste it over here and drag it over to the spot that I need it to be. Okay, so with H and O, H is the positive side, O is the negative side. That's going to mimic what I have right here. So I'm just going to paste it right here, right click and paste, or you can do Control V as a shortcut. I'm going to drag it until it fits right where I want it, right there. Okay, now this one's the opposite. Negative side is on the left, positive side's on the right, so I'm going to use this one. Copy, or you could hit Control C to copy it. And I'm going to paste it over here. I hit Control V to paste. And then I'll just put it right there. All right, and then I have this one, which is like this. So I'll copy that and paste it. Move it right here. And then this is just the same, positive on the left, negative on the right. So I'll paste it, and wherever it puts that arrow, I'm just going to drag it over. And then finally, I'm going to copy this one because the negative's on the left. All right, there we have it. Okay, so the arrow always points toward the atom that has the highest electronegativity value, and when two electrical charges of opposite sign are separated by a distance, a dipole is established. You might want to know that word dipole because we're going to refer back to it in the IMF notes. Okay, bond polarity versus molecular polarity. So this is where it gets a little bit different. We've been talking about the polarity of a bond. What if you have more than one bond? Well, we've got an example of that here in CO2. Okay, so in CO2, you've got a CO bond on the left and you've got another CO bond on the right. The CO bond is polar because the atoms have different electronegativities and the electrons are shared unequally. So the bond has what we call a dipole. We just defined that word on the last page. A dipole just means that it's got a positive side and a negative side. What we're showing here is a dipole. Now, the CO2 molecule is nonpolar. Now that sounds weird. The CO bond is polar, but the molecule is nonpolar. The reason is because the molecules can contain dipoles, actually two dipoles of the same magnitude. So they're just exactly the same thing, a CO dipole and another CO dipole. But they're pointing in opposite directions. So the dipole moments actually cancel out. Thinking back to a tug-of-war match, if we had this oxygen trying to take all of the electrons or kind of hogging the electrons and pulling them towards it, well, we also have this other oxygen pulling the electrons towards it. So there is no net dipole. It is a non-polar molecule because it's linear and they're pulling in opposite directions on the electrons. We have opposite opposing dipoles and they cancel each other out. H2O is different. H2O, we have an HO bond, which is a polar bond because the atoms have different electronegativities and the electrons are shared unequally. So the bond has a dipole once again. However, unlike CO2, the H2O molecule is polar because the molecules contain dipoles of the same magnitude. It's two dipoles of the same magnitude which do not directly oppose each other. If you look at the angle, remember that water, H2O, is a bent molecule, and that's because we have two lone pairs of electrons at the top. They're not shown in this diagram, but there's two lone pairs at the top. So geometry is really important to understand when you talk about polarity. If it's a bent molecule like this, even though we have these two dipoles, they don't cancel each other out. In fact, they combine to make one dipole like this, where we have a negative side on the oxygen side and the two hydrogens on this other end have a positive charge. It's because it's bent. They have two dipoles of the same magnitude which do not directly oppose each other, so the dipole moments do not cancel out. They combine. So let's go down here and look at some diagrams of some different ways that polarity can manifest itself. So if we have the dipole moments of two identical polar bonds pointing in opposite directions, they're going to cancel out. The molecule will be nonpolar. This is a linear molecule. If we have a bent molecule like this, the dipole moments, you see that they're going down at an angle. They have an angle less than 180 degrees. In other words, they're not linear. The sum of all the dipole moments is shown by the dashed arrow, this red arrow. So the molecule is polar. The dipole moments of three identical polar bonds at 120 degrees from each other, that's a trigonal planar arrangement, they're going to cancel out because they're all pulling in opposite directions. But here, in a trigonal bipyramidal arrangement, which would mean we have a lone pair at the top and three bonds, the dipole moment of three identical polar bonds at 109.5 degrees from each other in trigonal pyramidal arrangement, they're not going to cancel out, and the sum of all the dipole moments is shown by this red arrow. The molecule is polar. Now we have the dipole moments of four identical bonds at 109.5 degrees from each other. No lone pairs on this one. It's a tetrahedral arrangement. Those dipoles will cancel out because they're pulling in opposite directions on the electrons. So we kind of got a summary down here of what you can maybe deduce from looking over this. A molecule is polar when the dipole moments of all the bonds in the molecule do not cancel out. But a molecule is nonpolar when the dipole moments of all the bonds in the molecule cancel out, or when all the bonds in the molecule are nonpolar. So those are the two ways that a molecule will be nonpolar: when the dipoles cancel out, or when all the bonds in the molecule are nonpolar. So the only time you're going to see a polar molecule is when you have a polar bond that does not cancel out. We've got some examples down here. In all of these examples, we're talking about a central atom attached to only one type of outside atoms. So bromine is attached to only fluorine atoms in that example. Up here, phosphorus is only attached to chlorine atoms. That's what I'm talking about. All right, this is an example of a linear molecule, carbon dioxide. CO is a polar bond, but because they because it's a linear molecule with identical bonds that are directly opposite each other, it's nonpolar. BF3, now looking at this drawing, you wouldn't know the shape of it, so you need to be able to kind of analyze in three-dimensional space, what does this look like? Well, because there's no lone pairs, it's a trigonal planar shape like this, which we see in the ball and stick model, and each of those dipoles are opposed to each other. This is a nonpolar molecule. Now we have a bent molecule. All right, we've got two different dipoles, but they are not directly opposite each other. So those will combine to make a net dipole. They're going to combine together and it will be a polar molecule. They don't directly oppose each other. That is polar. All right, CH4, those are going to spread out and oppose each other directly because there are no lone pairs on here. This is a nonpolar molecule. On this one, I've got one lone pair that forces these down in a trigonal bipyramidal shape. And even though we've got three dipoles, they don't cancel each other out, so this is still a polar molecule. H2O, it looks linear, but you got to think in terms of three-dimensional shape. Those two lone pairs will make it a bent molecule like we see over here on the right. And because it's bent, those dipoles don't cancel out. This is a polar molecule. All right, this one is going to be nonpolar. There are no lone pairs, so all of the dipoles are going to cancel out. You see the lone pair on this one? So you can visualize these two dipoles kind of cancel out, but these two, they don't cancel. They're going to combine to make a dipole. This is a polar molecule, just like this one here. These two cancel each other out, but this dipole doesn't have anything to cancel it out, so this is a polar molecule. Okay, we have two dipoles here in opposite directions, and there's nothing else, so this is a non-polar molecule. SF6, all of those bonds, all 6 bonds are canceled out by another dipole, so this is nonpolar. In this case, these 4 will cancel each other out, but we have a dipole here at the top that is not canceled out by anything on the opposite side, so this will be a polar molecule. In this case, all 4 of those bonds are directly opposing another polar bond. So in a square a square planar shape like this, it's going to be a non-polar molecule as long as all the atoms on the outside are the same. All right, so it says here on the previous page, all the central atoms are bonded to atoms of the same element. But we want to consider situations when the central atom is bonded to atoms of different elements. So what we're saying is, in all of the examples above like this, like XeF4, you've got a central atom and it's bonded to 4 different fluorine atoms, but it's all fluorine. All of the outer atoms are the same. This is a situation where the outer atoms are different. Let's think about this. And we're going to use the example below. For the molecule below, we're going to draw arrows showing the dipole moment of the bonds and use electronegativity values to guide the direction of the arrows. Now, the electronegativity values are given here. I know it's going to be really hard for you to draw an arrow on here. If you're doing this on paper, go ahead and do that. But if you're doing this on Google Docs like I am, you don't have to draw the arrow. We're just going to talk about it. So H has the lowest electronegativity. C is a higher electronegativity. So the cross end of the arrow would be on H, and the pointed end of the arrow would be on C. We'd have another dipole where the crossed end would be on carbon because it's the lower of these two, and the arrow would point toward the N. All right, so that would mean that those 2 dipoles are actually going to combine together, pointing in the same direction. I've got this one that's pointing towards the carbon, and I've got this carbon as the more positive side, and it's pointing toward the nitrogen. Those 2 dipoles will actually combine together. So the question down here is HCN polar or nonpolar? HCN is polar because the two dipoles would combine together in the same direction. In other words, they don't cancel each other out, right? And we're not going to worry about the COF2 molecule, as I said. All right, so conclusion from the example. When the central atom of the molecule has no lone pairs, so the central atom has no lone pairs, and it's bonded to atoms of the same element, the molecule is nonpolar. Okay, so when the central atom of a molecule has no lone pairs, it's bonded to atoms of the same element, the molecule's nonpolar. When the central atom of a molecule has one or more lone pairs, it's usually going to be polar. The lone pairs usually make it bent or trigonal pyramidal. It usually takes it in a shape that is naturally polar. Okay. There are a couple exceptions. The exceptions are when you have 2 bonds and 3 lone pairs, then the molecule will be nonpolar because that's linear. Okay, so if you can remember that it's linear, that makes sense. But 3 lone pairs, 2 bonds, it's usually going to be nonpolar because it's linear. Unless they're 2 different atoms like it is here. Okay. When there are, let me think here, when there are 4 bonds and 2 lone pairs, that's a square planar arrangement. So looking back up here, this one, 2 lone pairs, 4 bonds, is a square planar shape. Remember, they opposed each other. You have a nonpolar bond. Okay, and the final point, by the way, I highlighted this because this, if you can remember this, you'll be able to answer any questions that I can throw at you. Okay, when the central atom of a molecule is bonded to atoms of the different elements, then the molecule is usually going to be polar, and you're not going to be dealing with exceptions to that in pre-AP chemistry. You might see some in AP chemistry or in college chemistry classes. But as of right now, if the central atom of a molecule is bonded to atoms of different elements, the molecule is usually going to be polar. So we're talking about something up here where you've got a central atom and then you've got 2 different outside atoms, 2 or 3 or however many. Usually that's going to be a polar bond. All right, that's it for polarity. The next video is an application of polarity, which is intermolecular forces.